Okay, so before we get into the physics, I want to briefly explain my presentation style. Ever since I decided to present these math videos in front of the camera instead of screencasting them, I've been faced with the difficulty of trying to present technically advanced content without a teleprompter. It's extremely difficult for me to remember very many technically complicated lines at once, and as a result, some of my last few videos have been recorded almost one sentence at a time. To smooth out the recording, but still deliver a nice visual presentation, all without a teleprompter, I'm trying this format, inspired by an old Vlogbrothers video. With this format, I simply use my raw intellectual power to will quantum field theory knowledge into your heads without speaking. Anyway, now for the physics. In my last quantum field theory video, we learned about spontaneous symmetry breaking, the Goldstone theorem, and the Higgs mechanism. We covered a global ON theory that gave a clear demonstration of the Goldstone theorem, and we also covered a U1 example that demonstrated the Higgs mechanism. The U1 example was definitely consistent with the Goldstone theorem, but because U1 has only one generator and the theory only one gauge field, it wasn't as satisfying a demonstration of the Goldstone theorem in the context of the Higgs mechanism as a theory with a larger symmetry group, multiple generators, gauge fields, and only partial symmetry breaking would be. With only partial symmetry breaking, only some of the gauge fields become massive, leaving some of the gauge fields massless. The gauge fields that become massive via absorption of a Nambu-Goldstone boson correspond to the generators of the broken symmetry. The gauge fields that remain massless correspond to the generators of the remaining gauge symmetry. And as per Goldstone's theorem, there are as many broken generators / Nambu-Goldstone bosons / gauge bosons that become massive as there are fields set equal to 0 in the new vacuum about which we are expanding the Lagrangian. Such a satisfying explicit demonstration of Goldstone's theorem in the context of the Higgs mechanism is the topic of this video. Specifically, we'll be handling this SO3 gauge theory, which will convert to an SO2 gauge theory via spontaneous symmetry breaking. Given the scalar potential, we have this set of non-zero scalar vacuum solutions from which we will make the standard selection. We can then construct the usual field reparameterization, followed by the gauge transformation that absorbs the Nambu-Goldstone bosons into the corresponding gauge fields. The two tasks of gauge transforming the Lagrangian and inserting the reparameterization can of course be done in any order, so we'll choose the easiest order to handle algebraically. That is, we'll gauge transform first and then insert the gauge transformed field reparameterization. Because the original Lagrangian is gauge invariant, the gauge transformed Lagrangian is simply what we started with. We can then insert the gauge transformed field reparameterization. From here, it's just a matter of reorganizing the Lagrangian via algebraic manipulation. Let's do this in pieces. First, we'll rewrite the first term, excluding the factor of a half. The first step is to insert the covariant derivative formula. We can then expand out the I-index sum and eliminate some of the derivative terms based on the fact that the off-diagonal terms of the Kronecker delta are 0. Next, we can expand out the A sum and insert the generator components from the matrix representation that I included in the statement of the theory. The next step is to expand out the squares and then refactor what we have to make the vector boson mass terms and the interaction terms clear. At this point, inserting this back into the Lagrangian density gives us this. The other part we need to rearrange is the scalar potential term. The first step is to simply multiply out all the powers, then we can refactor by power of sigma. Constant terms make no difference to the Lagrangian, so they can be dropped. Next, we can simplify the mass term and eliminate the linear term in sigma by inserting the value of v. We can then insert this back into the Lagrangian to get the final spontaneously broken Lagrangian density. This Lagrangian is kind of a mess, so before we discuss it, let's define the following masses and break it into pieces. As we expected based on Goldstone's theorem, the two gauge fields corresponding to the two spontaneously broken SO3 generators became massive, and one gauge field remained massless, corresponding to the generator of the still unbroken SO2 symmetry. And with that observation, we're done. I hope you enjoyed this video, or at least found it interesting. If you did, please consider sharing it with a friend, giving it a thumbs up, and subscribing.